Greetings, everyone. I'm Aditya Raj, and today I'm joined by my teammate Akash Nayak. And today we'll be delving into the world of Twitter. And we have performed an in-depth social network analysis. So we have completed this project under the guidance of Dr. Animesh Chaturvedi, sir. So let's start off with the introduction. So Twitter is one of the largest social media companies in the world, along with Facebook and LinkedIn. To manage the level of complexity which Twitter handles, there's a large network of complex web graphs inside of itself, forming a huge social media network. We have performed an in-depth social network analysis, also known as SNA, with the help of the frameworks Hadoop, Spark, and GraphX, and have derived multiple useful results. So let's look at the details of the data set. We have sourced this data set from the Stanford Large Network Dataset Collection and have considered 3 out of the 4 data sets. These data sets described all of the interactions which happened on Twitter about the Higgs boson particle between the 1st and 7th of July in 2012. And all the graphs that we have considered are directed. So let's look at the details of the data set. The 3 graphs which we have considered are the social network graph, the retweet network graph, and the mentions network graph. And you can see the nodes and number of edges here. Moving on to algorithm definitions. So we'll start off with page rank. So page rank is actually basically a rank of the most high quality page. It also considers the number and both the quality of links, which we had not considered in our previous project in graphs in data structures. So here there is something known as damping factor, which we have taken as d is equal to 0.85, and it marks the probability that a user will select the next page from one page. So next we have connected components. Connected components are basically a subgraph in which when you select one node, you can definitely reach another node which you select. If you can, then it is a connected component. If not, then that becomes a completely different subgraph. Moving on to degree of centrality. Degree of centrality is defined as the number of degrees divided by the number of nodes in a graph. Next, we move on to triangle counting, which is a very complex algorithm to actually implement. So in triangle counting, we basically try to look for the shape of triangles, but in the form of nodes and edges. So one node will be connected to other nodes, which will then inherently be connected with each other. So forming a triangle. It also helps in basically finding clustering. Next, we have closeness centrality. This is actually the reciprocal of average of all the closest paths in a graph. So let's discuss the configuration which we have used for computation. So we have actually used both the Hadoop single client and multi-node cluster system, depending on the type of computation and algorithm which we are running. So in this, our storage medium was the Hadoop distributed file system, HDFS, and it allowed basically for shared storage media when required in multi-node setups. Okay, so let's look at the framework which Hadoop uses to distribute the work, and that is Yarn. We didn't actually use this, but what Yarn actually does is it basically distributes whatever task given to it into multiple processes and divides it to all the nodes in the cluster. We found a better alternative, which is Spark. Spark basically uses HDFS as a storage media. It takes in the data from HDFS, it processes it, it divides the work using its resource manager, and sends it back to HDFS using output data. We ran GraphX algorithms on Spark basically to enable multi-node computing. So we compare Spark and Hadoop's MapReduce here. So Spark is actually much faster than MapReduce. It is written in Scala and it can perform not only just batch processing, but it does real-time, iterative, and graph processing as well. So due to this massive speed advantage, we decided to go for Spark over Hadoop's MapReduce and only used Hadoop for HDFS. So let's look at the HDFS file here. In this HDFS file, we just used, we put a simple edges and vertices file inside of our HDFS directory. And while using closeness centrality, which will show you, whose result will show you later, this was the load which was put onto our 2 nodes which we selected. Okay, so now let's look at the major issues with running a single client setup. So basic algorithms like PageRank, connected components, and degree centrality work on single node clusters without any issues, except for the times when network lag is present. But as soon as complicated algorithms like closeness centrality and triangle count are introduced, single client systems do not work any longer, which leads to the requirement of multi-node cluster setups. So looking at the error messages which we got, and you can immediately see that most of them are memory related, as our single computer did not have enough compute power in itself. So as soon as these complicated algorithms came into play, we immediately had to switch to a multi-node setup. Moving on to Akash for a multi-node cluster Spark demo for triangle count.
Yeah, so thank you, Aditya. We had some limitations on Mac OS, so that is why we are switching our system to Ubuntu. And here we are running our algorithm triangle count on a distributed system. So let's start with the Spark shell. Our Spark shell is getting started. Going back to the shell, let's run our algorithm. So here we are importing the packages that were required to calculate the triangle count. This is the initial time of start. we are also calculating the time taken by the algorithm to run. So here our graph is getting loaded. You can see this is the try count object of the Spark graphics, which we are using to calculate the number of triangles. We are also importing the Twitter ID.text, which has the IDs of the users from HDFS. And then we are joining the triangle counts, which we had calculated by triangle count object, and then joining it with the users. So here you can see the running applications. You can see two workers, two nodes, which are working. So here you can see that two nodes are active. You can see the number of cores and active tasks. So let's go back to our shell. So here you can see that the number of triangles which were calculated for the users are being sorted in descending order. Here our result is displayed. You can see the number of users who have been arranged in descending order based on the number of triangles. The time taken to execute this algorithm is 238 seconds on two nodes. Yeah, so as we have a bit of time crunch, so we'll be just going through the results of the further algorithms. The codes and configurations for all these algorithms could be found on our GitHub. So the first one is the PageRank algorithm. So in a social network, the PageRank gives the most popular or influential person present in the social network. So it uses both quality and quantity of the edges to calculate the PageRank. And here you can see that the user with ID 241841 has the highest PageRank, that is 1. So coming to the next result, that is the connected components. We have used the connected components algorithm of graphics to find the clusters in the social network. So here are the top 10 clusters in the social network arranged in the order of decreasing order of the size of the clusters. So here the component ID is basically the lowest numbered node present in the cluster, and size is the number of nodes present in that cluster. So in this graph, you can see that the cluster having component ID 1 has around 5 lakh nodes, but the later clusters that are these with IDs 321684 and so on have very few nodes within them, that is less than 10. So this tells that the users who were interested in the content related to Higgs boson particle managed to connect with each other over the 7-day span. The next result is about the number of retweets received by the users in the social network. We have used the in degree method of graphics to find the number of retweets received by an user. So we are displaying the top 10 users based on the number of retweets they have received in decreasing order. So this shows the extent of popularity of any post a user is pushing in a short span of time. The next one is the number of times a user is mentioned in the social network. We are displaying the top 10 users based on the number of times they are mentioned in the social network in a decreasing order. So the user with ID 88 has the highest number of mentions, that is 11,953. In the next result, total degree count, we are finding the total degrees of each node in the social network and arranging them in a decreasing order and displaying the top 10 users. This shows how well a user is connected in the graph. While calculating this, we use only directly connected nodes. The next result is about the influential users in the network. Considering the degree of centrality, the degree of centrality is basically obtained from the total degrees of a user in the network. So the degrees of centrality is just the normalized form of total degrees, which ranges from 0 to 1. Coming to the next result, which is the triangle count. We have already seen the demo of this algorithm. So the result displays the user ID and the number of triangles. We have displayed the top 10, considering the number of triangles they have. So it's actually a measure of clustering where the numbers represent the tightly connected communities within the network.
Okay, so now let's look at the next set of results which we have received from our multi-node cluster setup, and that is closeness centrality. So closeness centrality is a way of detecting the nodes which can efficiently spread information throughout a graph. Here we decided to implement this algorithm on the mentions network dataset as we wanted to compare it to how strong it is in spreading information to retweeting. But we actually arrived at this very surprising result where all of the nodes are giving us a result of infinity. As you would have already seen before in the math, that closeness centrality is defined by a number of nodes divided by all the shortest path in the graph. So The result is quite surprising, as you would have seen, but there is a simple reason as to what we think is the reason we are getting infinity. We would have already seen before that most of the nodes are already connected in the graph, but we also know that mentioning someone is not the same as spreading information to everybody, and rather it is only from going, or the information is only going from point to point. Therefore, mentioning can only be from one to one node, or it can be from one to many nodes. So from this, we can see that actually mentioning someone is not a reliable way for spreading information. It will fail immediately as soon as information will be passed around from one community to another. So let's take an example of, let's say, a person in the sport community would like to spread something into somebody in the academic community. Since there is no link or no edge between these two communities, no shortest path can be generated between those two nodes or users in this case. Therefore, failing the spread of information from this community or that person to another person in another community. So rather than mentioning, a person would initially first have to create some type of connection, which would be in this case on Twitter, the act of following, to actually create an edge first and then pass some type of information from one node to another. So moving on. So the first future work that we can actually continue to do in this project is operating system compatibility, increasing compatibility with other operating systems other than Ubuntu. Unix-based systems have very less support in terms of Hadoop and Spark. Example, Mac OS, like our systems, and we have to eventually switch to Ubuntu to actually make multi-node clustering work. In communities where we have multiple large clusters of people, like two clusters of people, we can actually make a gateway between two nodes and basically form a recommendation engine for one person to join another community. This will allow users from one community to find another community, not between just one and one user, but actually multiple users connected to that one user can then get recommended that community. Then we can also try to design an algorithm which can scan the network prior to running a task. So basically, while we were executing our multi-node setup, we found that as soon as the number of nodes increased, actually the performance went down as there would be a lot of network lag. So that's why we went with two node setup altogether. So if we actually run this algorithm, we'll be able to actually tell that, okay, if we run two node setups, it'll actually be better than three, or if we run four node setups, it'll be better than two. And if it is more, then it will basically help in optimizing for speed. And if it is less number of nodes, it'll help in optimizing cost. So that's it from our side. Thank you.